So we're going to be looking at estimating population means today. So to estimate, when you're doing a population mean, you're going to be working with quantitative data. So data that you are actually measuring, like for instance, you're looking at height of all the kids in the school, or you're looking at average test scores, but you're not looking at like hair color. So you're looking at quantitative data. You can use the one sample z interval that we use for proportions, but that's very, very rare, mainly because that's not helpful. If I don't know mu, then I probably don't know sigma. So I'm working with a population here where if I'm estimating the population mean, which means I have no idea what the population mean is, and if I don't know what the population mean is, then I probably don't know what the standard deviation of that is. And so my one sample z interval won't usually work. I can't just substitute in the sample standard deviation because my intervals won't always capture the true value. Basically, my intervals won't be quite as long as I need them to be, so they won't always reach, like let's say I was at 95% confidence, my intervals might be at like 92% or 91%. They won't reach my percent of confidence. So what I need to do is I need to increase my critical value. Remember when we were calculating our proportion, we used our critical value z, okay, and we got that from our table A. And if we used our critical value z for these, our intervals basically this wouldn't be quite big enough. So we need to increase the critical value. So what we're going to be looking for is we're going to be using the critical value of t, and we'll be doing what's called a t distribution. Okay, so let's look at what we can do with these t distributions. So when my sampling distribution of x, so that's this one over here on the left side here. So when my sampling distribution of x, and remember what a sampling distribution is, right? This would be a dot plot, right? And I can't draw dots in a straight line, okay? But this would be, right, all these different samples. I'd have the mean of a whole bunch of different samples, right? And that's what this graph over here of my sampling distribution is. So the mean of a whole bunch of different samples. So my sampling distribution of x, okay, if that is close to normal, then we can find probabilities involving the mean of x by standardizing. We can take, sorry, I didn't have the right, okay. So we can take z and we can standardize it. We can subtract mu and we can divide by our standard deviation formula. Okay, and so when I standardize that, what that's going to do to the shape of z here, okay, so what that will do is that will, when I subtract by mu here, okay, that's going to take me down to a mean of 0, right, because my population and my sample mean should be, my sampling distribution mean should be the same. And it doesn't affect my shape or spread. So basically what this part does right here, okay, is it moves my mean to the left by mu units. Okay, and so and then when I divide, by the constant here, okay, the sigma divided by the square root of n, that keeps my mean at 0, okay, but it makes the standard deviation 1, and remember, so it affects the spread, but it doesn't affect the shape. So when I standardize my data points, that makes my standardization here have basically a standard normal curve. That's what you see happening right there. Okay, so I get a standard normal curve. And when I standardize it, I can use the sample standard deviation, which will give me a slightly bigger spread than a normal curve. And that's what my t distribution is. Let's look at that. So let's look at this graphic right here and help make a little bit more sense of this. So what we've done here is a Fathom simulation, okay, and so I've got a sample mean and 550 simple random samples. So these are sampling distribution graphs right here, okay, and so this top one here has been standardized, and we use the standard deviation of the sample to do that. Okay, so we use the standard deviation of the sample to do that. If the bottom one it was standardized by using the standard deviation of the population. So I get this pretty normal curve. The top one, again using the statistic, the standard deviation of the statistic, still gives me a relatively normal shape in the sense that it's roughly symmetric. Okay, it's a unimodal, but you'll notice that the spread is bigger and there's more area under the ends of the tails. So basically what it means is that my distribution here has a bigger spread. It's a little bit wider, and that is my t distribution. You can see it here on the probability plot. Okay, this is using the standard deviation of the population, so this one right here, and this is using, the first one is using the standard deviation of the sample, which is this one here. So you can see it would have a bigger spread and a little bit more area under the tails. You can see that here when you kind of layer these curves on top of each other. Okay, so my t distributions, they are the red dotted line, and they are the red dotted line and like the turquoise line. So you can see they have that same basic shape, roughly symmetrical, one single peak, so unimodal. Okay, but you'll notice they're not quite as tall as the normal curve. The purple one is taller. It's a little bit more narrow with less area under the tails. Those red and turquoise ones there have a little bit more area under the tails. So they're a little bit wider. Okay, so you have your summary here. Right, and this is going to involve our degrees of freedom, this t distribution. So when we are drawing a t distribution, we're taking an SRS of size n from a large population that has a normal distribution. So the population has to have a normal distribution. Okay, I need a sample size n with a mean of mu and a standard deviation of sigma. The statistic, so right here, has a t distribution with degrees of freedom n minus 1. So this also is different from our z samples. Okay, we have degrees of freedom are coming into play now. Remember, degrees of freedom are n minus 1, so our sample minus 1. When the population distribution isn't normal, this statistic will have approximately a t n minus 1 distribution if the sample is large enough. Okay, so I could have a population distribution that isn't normal, and I can still use this as long as my sample size is big enough. Okay, similar to what we saw before. So when we interpret this the same as we would any other standardized statistic. Okay, it tells us how far the mean x there is from its mean u. So from the population mean in standard deviation units. Sorry, I wish this was a little neater. Okay, so keep in mind when we're doing this, right? Our sample mean x follows our normal distribution. So our sampling distribution follows our normal distribution. But your standardized t statistic follows that slightly wider t distribution. So that would be when I use the statistic. Okay, I interpret that statistic the same as I would any other standard statistic. And so it tells us how far the mean x is from our mean of mu. Okay, each sample size is going to give us a slightly different distribution. Again, that's going to depend on the sample size. So we're going to have to specify our degrees of freedom. Remember, our n minus 1. Okay, and that's going to give us our particular t distribution n minus 1. Okay, so again, they're all going to be slightly different depending upon the sample size. So let's look at how we can figure out what this would be, what this critical value t would be for our different confidence levels. And to do that, we can use table B. So let's look at an example that works with that table for us. Okay, so what we have here is using table B, what critical value t star, t asterisk, from the table B should be used in constructing a confidence interval for the population mean in each of the following settings. The first one I've got a 95% confidence interval based on a sample size of 12, and the second one I have a 90% confidence interval on a sample size of 48. So first of all, these two down at the bottom, those are little snippets of Table B. Okay, Table B, you have a copy in the back of your book as well as in your formula chart of the whole thing. So let's look at these little bits of Table B and see how we would read it. So they're going to give us the critical value, and that's what all the decimal point numbers in there are, the 1.812, that kind of thing. What we have on the left is going to be our degrees of freedom. So over on the left of the table, you're going to have the degrees of freedom. So for the first example here, I've got my degrees of freedom are n minus 1. So I'm looking at the 11. And then you'll notice down along the bottom of the table are some of our more common confidence interval levels that we would need. Okay? And so this one we want 95%. So our critical value here, our T star here, is 2.201. Okay, the other way you could do that is across the top here also is my tail, right? And remember, if I have 95% confidence, what I have left over under the tails is 2.5% on each side of the tail. So my area on the left, under the right side of the tail is 0.025, as well as on the right tail is 0.025, and on the left tail is also 0.025. For part B, I want a 90% confidence interval, so that'd be an area of 5% on each side, or 0.05 on each tail. Okay, 90% confidence level. But my degrees of freedom here, you'll notice my degrees of freedom are going to be n minus 1, which is going to be 47. And you'll notice I don't have a 47 on the side of my table here. So when you don't have the appropriate degrees of freedom number, you need to use the closest but not greater. Okay, so I can't use 50. I'd have to use 40. So my critical value that I would use here would be 1.684. You can also do this using technology, which I would strongly recommend. If you don't have the appropriate confidence interval or area on the table, you definitely need to go ahead and use your technology. So when you're using your technology, you're going to be at, let me get rid of some of this so you can see it. You're going to use another inverse formula. So when you're using technology, you're going to use inverse T. Okay, and then you're going to give the area to the left of your desired critical value. So we'll walk through an example of this in just a second. And then the next one would be your degrees of freedom, and that's it. So like for A, if I was finding my critical value in my calculator for A, I would have inverse T, my area would be 0.025, my left tail basically, and my degrees of freedom would be 11. And I don't have room to write out, there we go. And so if I was doing the second one, I'd have inverse T, parentheses, area, 0.05, and then degrees of freedom, 47, and it will spit out your critical value of T. 7. So just like with proportions, there are some conditions that we need to meet before we can go ahead and construct our confidence interval for mean. So the first thing is that the data needs to come from a random sample or a randomized experiment. So we have to be sure that it's random. We also need to check our 10% rule. When we're sampling without replacement, which we usually are doing, okay, we need to double check that our sample is less than 10% of our population. And remember that way then we can use our formula here for calculating standard deviation. The next thing is that we need to check whether it's a normal Okay, so let's look at this example here to see whether we can actually use the t-distribution or not, if we can use a t-critical value to determine our confidence interval. So the first one here, okay, we are estimating the average GPA of students at your school. You randomly select 50 students from the classes that you take. The first graph there is a histogram of their GPAs. So when we check our conditions to see whether we can use our t-distribution, for this one, we would say that no, we could not, because it does not fit that condition of being random. The 50 students were selected from the classes that you take, not from the entire school, so it would not fit the random condition. The second one here, B, is asking about the force it takes to pull wood apart. The second graph there is a stem plot of the force in pounds required to pull apart a random sample of 20 pieces of Douglas fir. So if we look at the stem plot, what we would see here is that we would not be able to use this data for use a t-critical value to build this confidence interval, because what I have here is a strong skew to the left with some possible outliers down here on the end. And remember, if we have a strong skew or we have outliers, we cannot use the t-distribution. The last one here, part C, shows us a box plot here, and we're wanting to estimate the mean SAT math score at a large school. I have a box plot of their SAT math scores for a random sample of 20 students at the school. So for this one, we would say that we would be able to use this. It does meet our conditions of random. While it's not a large sample, nor do we know the shape of the population distribution, when we look at this graph here, okay, we can see that it would have a moderate skew and no outliers. So we would assume that we could go ahead and use our t-distribution here. There is no hard and fast set rule for a moderate versus a strong skew. So in the problems that you see on your AP test, in your regular tests in class, it will be very definite, just like it was here. You'll either have like all the way to one side or the other, or pretty close to the middle, so that you'll be able to make a pretty easy determination whether it's a strong skew or a moderate skew. Okay, so now that we've checked conditions, let's look at the actual construction of the confidence interval for the mean here. So when we do this, we're going to be using the standard error of the sample mean. For those of you that have taken AP Bio, we've talked about the standard error of the mean. They're the same thing. So the standard error of the sample mean, this is how we're going to calculate it. Right, we're going to take our sample standard deviation, that's what the SX one is, and divide it by the square root of our sample size. Okay, it's going to describe, again, how far the mean X will typically be from mu in repeated SRSs of that same sample size. Okay, so when we construct our confidence interval, it's going to be the same as it was before. We're going to take our statistic, which in this case would be the mean from our sample. We're going to take our critical value, which is going to be using our t-distribution, and we're going to multiply it by the standard deviation of the statistic. And this is called our one sample t-interval for a population mean. So we've seen a one sample z-interval for a proportion, and now we're seeing a one sample t-interval for a population mean. Remember, when you're doing your problems and you have to plan and tell what method you're going to use, you're going to need to use these appropriate names. All right, so let's look at some examples of these, and then we'll look at how to calculate a sample size again with margin of error, and we'll be all done. Okay, so this example here involves auto pollution, and to save time and shorten up your video a little bit, what I would tell you to do right now is pause it and read the problem real quick so that you can follow along with the solution and the example. Okay, so whenever we solve one of these, just like we did for the z proportion ones, the one sample z proportion, we have our 4 steps that we need to do. Remember, our steps were to state, plan, actually do the calculations, and then do our conclusion. So for part A here, where it tells us to construct and interpret a confidence interval for the mean amount of NOx nitrous oxides emitted by light-duty engines of this type. So again, remember, our steps are to state, plan, do, and then conclude. So let's do step 1. Let's do our statement here. So if we're going to state what we're doing here, we're going to state that we want to estimate, because this is what we're going to do, right? We want to estimate the true value, the true mu, the true value of the mu if you want, of NOx emitted, and again, this is where we get into our context, right? Emitted by light duty engines of this type, and we need to state at what confidence we want to be at as well. Okay, at a 95% confidence level. Okay, and that would be step one. So what are we going to do? Okay, we're looking to find out what our true mean is, okay, for this, and we want to have a 95% confidence level. So our step two then would be to plan that out. So what are we going to do to be able to calculate that? Oh, it's going to erase my steps on the corner. All right, so step two then, I'm going to plan. So my plan here, I need to say what method I'm going to use, right? And so I'm going to construct, because that's what I'm going to do, I'm going to build it, a one sample T interval if conditions are met. So I'm going to need to check and make sure that those conditions are met. And this is where I would do that, right? So my conditions are that it is random, okay? And it's stated that I took a random sample here, okay? I need to check my 10% conditions because I'm not putting these back in to the population. So I need a sample, I need a population of at least 400, and the assumption would be that there are more than 400 light-duty engines of this type out there. And then I need to check normal or large sample. It doesn't tell me the distribution of my population. However, my sample is 40, which is greater than or equal to 30. So I'm going to assume that my sampling distribution is approximately normal. So my conditions are met, just like we said before. The problem isn't set up for my conditions not to be met, but I need to be able to prove that those conditions are being met. Okay, step 3 is the actual doing. So the calculations, the showing of your work. Okay, so we were given the sample standard deviation, which is 0.332. We were given the sample mean, which was 1.2675. Okay, remember for t distribution, we need our degrees of freedom, which would be 40 minus 1, which is going to be 39. Okay, I'm going to use my calculator to do this because my table B doesn't have a 39 degrees of freedom. So I'm going to use my calculator just because I think that's a better option when I'm doing that. So my area, because I'm at 95% confidence here, right, that leaves 5% in total, so my 2.5% in each tail. So my area is 0.025, and my degrees of freedom is 39, and that's going to give me, that gives me a t equals negative 2.023, which makes my critical value of t is my positive value of that, just like it was for the z. So my critical value of t is 2.023. And so then I'm going to be able to plug that into my formulas. So when I plug that into my formulas, let me give myself some space to do that. Okay, here we go. So when I plug that into my formula, I get my statistic, which is 1.2675, plus or minus my critical value, so 2.023, times my standard deviation of the sample over the square root of my sample size, over the square root of 40. And when I solve all that, I get an interval of 1.1609 to 1.3741. Okay, so there's all my work for this. So now I need to do step 4, which is my conclusion. Remember our statement here, it's the same as it was before. We are 95% confident that our interval that we calculated, so that the interval 1.1609 to 1.3741 grams per mile. You can put some units in there, again for context. Grams per mile captures, and what are we trying to capture here? We're trying to capture the true mean of NOx emitted by these light-duty engines. So captures the true mean of nitrous oxides emitted by these particular type of light-duty engines. Remember, do not shortchange your context answers. Okay, so let's look at another example here. Again, take a second and pause it and actually read it so you can follow along with the solution. You also might want to consider, as we go through each step, pausing it so that you can do it yourself and then double check to see if you got it correct. Okay, so here we go. We're constructing and interpreting a 90% confidence interval for the mean tension mu of all the screens produced on this particular day. So my first step, again, is to state what I'm doing. Okay, so if I'm going to state what I want to do here, we want to estimate. So again, the same as it was, starts the same every time. We want to estimate the true value of mu, of the mean, of wire tension, because now we have to put it into context here, of the video terminals that were produced on that particular day. You have to make sure that that is put in there. So for the video terminals produced that day, because our problem specifically says that it's looking at one particular day's work worth of production here, and we are at, and this time we're at a 90% confidence level. Don't abbreviate on your AP test. Okay, but we are at a 90% confidence level instead of a 95. So from here I move on to the planning stage. So we will plan to be using a one sample t interval, because I'm calculating mean here, if my conditions are met. One sample t interval distribution, t distribution. Okay, if my conditions are met, so if we check those, okay, it says it's a random sample, so we're met there. 10% conditions, so assuming that they made more than 200 video screens that particular day. Okay, and then we need to check our normal large sample conditions. Okay, well, our sample doesn't, we don't know our population distribution, and our sample is equal to 20, which is less than 30. So now I have to move on to that graph stage. Okay, so if I put this into the calculator, these are the graph options that I would get. Okay, let me do this. So these are some of the graph options that I would get here. If you encounter this on your AP test, you cannot just say that you did a graph on your calculator. You're going to need to sketch at least one of them. You don't need to sketch all three of them, but you will need to sketch at least one of them. So as I look at all three of those, I don't see any kind of strong skew with any of them. I don't see any outliers with any of them, and my normal probability plot is roughly linear. So I can go ahead and assume that this is a normal population. So my conditions have been met, and I can move on to step 3. So in step 3, I need to show my work and my calculations here. So step 3 here, my mean is 306.32. This was not given to me. I went ahead and I put it all in my calculator in list 1. Okay, and then when I pull up my statistics for list 1, I get my mean of 306.32. I'm using the standard deviation of my sample. Okay, you are not using that one. You're using the standard deviation of your statistic of this sample. Okay, when I put it into my calculator to get my critical value, I've got my inverse t. I'm at a 90% confidence level, so I've got a leftover area of 10%, splitting that at both tails. So I get an area of 0.05. I get my degrees of freedom are 19, right? 20 minus 1 is going to give me 19. So this gives a t value. That gives a t value of negative 1.73, which makes my critical value 1.73, not negative. Okay, so when I plug this into my formula, remember in my formula, I've got my statistic, so my mean of my sample, plus or minus my critical value of 1.73 times the standard deviation of my sample divided by the square root of my sample size. And when I solve for that, I get a confidence interval of 292.31 to 320.33. Okay, so when we move on to step 4, we get our conclusion. So our conclusion is our blanket statement. We are 90% confident that the interval 292.31 to 320.33 captures, and we're looking to capture the true mean, and then I put that in context. So the true mean tension of all the video terminals produced that particular day, because we cannot draw conclusions about other days because we were only pulled from that particular day. So the true mean tension of all the video terminals produced that day. So just like we did for proportions, we can also determine a sample size for a desired particular margin of error when we're estimating the mean. Okay, our formula for that is going to look like it did before. So we're going to take our critical value, okay, and we're going to multiply that by our standard deviation over the square root of our sample size and set that less than or equal to our margin of error. And we're going to get a, basically we're going to need some values to be able to do this. So we can either get a reasonable value of our standard deviation from either an earlier or a pilot study. That would work, that would be okay. We can get our critical value from a standard normal curve for a particular confidence level. Okay, and then we'll go ahead and we'll set that, again, less than or equal to the margin of error. So let's look at our example with this and kind of put this into action. So this example uses monkeys. There's researchers would like to estimate the mean cholesterol level of a particular variety of monkey that's often used in lab experiments. They want their estimate to be within 1 milligram per deciliter of the true value, and they want to be 95% confident. Okay, and they want to know the sample size of monkeys that they would need. They've done a previous study that involved this variety of monkey, and this gives a suggestion that our standard deviation should be about 5 milligrams per deciliter. Okay, and so they want to know the minimum amount of monkeys they're going to need to be able to conduct this study and get a good estimate here. So we're looking for 95% confidence with this. Okay, and we have a critical value of z is 1.96 because we know that's what it is for 95% confident. Okay, we've done it a number of times. It's in our table. We can put it in our calculator. So we know that our critical value when we want 95% confidence is 1.96. Okay, we can use a standard deviation of 5, which they got from that previous study that they did before, and our margin of error is 1 deciliter. Okay, so our margin of error is only 1. So when we plug this into our equation, we get our critical value, 1.96, times 5 divided by the square root of our sample size. Okay, and I want that to be less than or equal to 1. When I divide both sides by 1 and multiply by my multiply both sides by the square root of n, I've got that my square root of n, I've got 1.96 times 5 divided by 1 is less than or equal to my square root of n. Square both sides, and I get 96.04 is less than or equal to n. So monkey-wise, I'm going to need 97 monkeys. Remember, when we're finding our sample size, we always round up. If we chose 96 monkeys, even though we're at 96.04, if we chose 96 monkeys, we'd have a margin of error greater than 1. So we have to go up to 97 monkeys to ensure that we'll have a margin of error less than 1. Okay, so we'll do some work with these in class and hopefully get any questions cleared up.